1.2 Radioactivity 1. Origin and nature of nuclear radiation. Alpha, beta, and gamma radiation all come from the nucleus. That's why we call them nuclear radiations. In fact, alpha radiation is just a stream of positively charged helium nuclei. Beta radiation is a stream of fast-moving, negatively charged electrons. And gamma radiation is an electromagnetic wave of very high frequency and hence very high energy. Let me emphasize one more time that they all come from radioactive nuclei. 2. Sources of radiation. The school has weak sources like americium and radium for physics experiments. They are sealed sources with wire gauze to avoid direct contact. Radioactive sources are stored in lead containers with warning signs and locked in a safe. When handling radioactive sources, we should use special leveling tools, which is a pair of special forceps. Do not direct the source to anyone and do not try to examine the source directly. Lastly, radioactive experiment should be as short as possible, with careful planning beforehand. B. Background radiation. We can never get rid of nuclear radiation, as a part of it comes from lateral sources. This is called background radiation. For your information, the background radiation in Hong Kong is about 100 counts per minute, which is at least 2 times that of Tokyo. 3. Ionizing power. Ionizing radiation can cause ionization, which means produce ion pairs. Ionizing radiation is so energetic that it can knock off an orbital electron from an atom and produce an ion pair. If it is a gas molecule, the gas is said to be ionized. With the ions, the gas may conduct electricity. If the radiation is stronger, there will be more ions and the gas will become more conducting. Nevertheless, different types of ionizing radiation have different ionizing powers. Example 1. Detector making use of ionization. The setup makes use of ionizing power of radiation. When the ions produced are attracted by the conducting plates, which are electrodes, there is current flow. The current flow will be larger if there are more ion pairs produced. For example, the beta source is replaced by the alpha source. Nevertheless, there will be no current produced in vacuum because there's no air in vacuum to be ionized. A spark counter makes use of the ionizing effect of nuclear radiation, and we may use it for measuring the ionizing power of radiation.
In this experiment, we will compare the ionizing power of alpha, beta, and gamma radiation using a spark counter. Connect the spark counter to an EHT supply. Gradually increase the voltage until sparking occurs. Then reduce the voltage slightly so that sparking just stops. Hold an alpha source about 1 centimeter above the wire gauze. Observe the sparks produced. Repeat with a beta source. Then repeat with a gamma source once more. Which kind of radiation produces the most sparks and therefore has the strongest ionizing power?
A spark counter counts the number of radiation when they produce ion pairs. The voltage between the electrodes, which are the anode and cathode, is high, but just a bit lower to ionize the air directly. When ion pairs are produced, the ions are attracted by respective electrodes and sparks are produced when they strike on the electrodes. The more ions are produced, more sparks will be produced. From the experiment, we can see that the ionizing power of alpha is the strongest, followed by beta, and gamma is the weakest. Alpha radiation is a stream of helium nuclei carrying 2 positive units of charge. The charge is the largest in the 3 main types, and alpha particles also move slowly, at about 10% of speed of light. These 2 factors explain its strong ionizing power. Also, sparks are observed randomly, and therefore nuclear radiation is emitted at random. This is called random nature of radioactive decay. 4. Seeing nuclear radiation. Nuclear radiation is invisible. However, we can trace their tracks and identify them using a diffusion cloud chamber. When an ionizing radiation such as an alpha radiation travels across a diffusion cloud chamber, it produces many ion pairs along its path. A cloud chamber is filled with saturated alcohol vapor which will readily condense on the ions. These alcohol droplets form that will reflect light and appears as bright spots to form a white track. Take a look of the experiment to see how a diffusion cloud chamber is prepared and what the tracks look like.
We are going to observe the tracks of alpha particles in a diffusion cloud chamber. This is a diffusion cloud chamber. Put some dry ice in its lower part. Cover the dry ice with a foam pad and screw the base lid back on. Use a dropper to add some methylated spirit to the felt ring in the upper part of the chamber. Replace the plastic lid. Illuminate the chamber with a lamp. Insert a weak radium source into the chamber and observe from above the tracks produced. Now, rotate the source so that it is behind the tin foil inside the chamber. Is there any change in the tracks produced?
Our tracks are thick and straight, which means alpha radiation can travel undeflected and produce a lot of ion pairs along its track. The tracks usually have different lengths, which mean the alpha radiation have different energies. Alpha particles are comparatively massive, and so it may travel in straight line. Its ionizing power is stronger, and so a lot of ion pairs are produced along its path. Beta tracks are scattered tracks. They are short and twisted, which means beta radiation can hardly travel in straight line, and their ionizing power is also weak, producing just a few ion pairs along its path. Beta particles are electrons. They are easily deflected, and so they can hardly travel in straight line. Gamma tracks are difficult to observe, as their ionizing power is the weakest. Instead of filling the chamber with air and alcohol vapor, scientists also try to fill the chamber with helium and alcohol vapor. It happens that an alpha particle collides with a helium atom to produce a right-angle fork, as shown.
The apparatus as shown is used to simulate particle collision. First, we spray the plastic beans over the tray. We are going to use the pair of magnets with identical mass to simulate the collision between two particles with the same mass. Push one magnetic puck gently to collide at an angle with the other one, which is stationary. What can you notice about the angle between the tracks of the magnets? Now we use a pair of pucks of different mass and repeat the experiment to simulate the collision between two particles of different mass. What happens if the colliding pucks have different mass?
From the right-angle fork, physicists deduced that alpha radiation has the same mass as a helium atom, since it has a strong ionizing power, and physicists also found that the charge is positive 2 units. They conclude that alpha radiation is in fact a stream of helium nuclei. Do checkpoint 2 on the next page.